So hello again, welcome everyone to this video. We're going to discuss more about relaxation factors in our introduction, in context of introduction to pimpleFoam. So in the last video we're talking about under relaxation and what it does. Oopsie, well, that's zoomed in pretty quickly. Okay, there you go. Yeah, we're talking about under relaxation, and basically, the idea is to get all the coefficients of this, to be less than 1. So we multiply this omega at the front so that we get all these coefficients to be less than 1. So it can be called omega online, can be called alpha, can be called phi, whatever. The idea is that you have this relaxation factor. So there's some you can either look at this source called Mathematics, Numerics, Derivations, and OpenFOAM, or you can look at this PowerPoint slide. I also put this in the slide below, in the what do you call that? The factor, no, description below. Okay, so they use this omega over here, and okay, so this x bar ik, this is the calculated value. Okay, so this is the calculated value. Okay, x calc, right? X calculated, which we are discussing before. This is the calculated value, and you plus 1 minus omega into xik minus 1. This is, of course, x old, where k is the iteration number. So you have the x old over here. That's exactly what we get. And in this okay, where is it? I better open this up. Okay, there you go. Open up this PDF, and I'll go this where you'll find the relaxation factor here is in chapter 12, I believe. Chapter 12, relaxation methods. You can see the formula is pretty much the same. It's slightly different here. Is phi n plus 1 equals to some phi n, which is the old value. This is it. And then this is phi n plus 1. So this is the calculated value. So in this case, we use alpha as the relaxation factor minus phi n. So phi n here is the old one. So of course, if you take this out, then you have 1 minus alpha times phi n. So this is where your 1 minus alpha actually comes from for this phi n. Okay, so field relaxation is in 12.1 for this document. Okay, so these are very useful what do you call that? Very useful resources you can find online. So what does it do visually, this relaxation? So for example, let's say you take a line, okay, and then you will have, okay, let's say on the first part of this line is x old, and then this is where x calc is. Okay, this is where x calc is, where x calc equals to, let's say, the 2 minus 20y minus 50z. Very easy numbers to remember, right? So between x old and x calc, if let's say this difference is very big, this difference is too big, and you have this this problem of the error multiplying. So what relaxation factor does is that when you see this being applied here, 1 over 100, you see 1 over 100, then you add 0.99 times the x old. So what does that mean? If your weighting factor is more towards the x old, okay, so you have what do you call this? A small relaxation factor. Small relaxation factor. So between your x calc and x old, all right, this will become x new. So it will take most of the value of x old and take very little of the value of x calc, and nevertheless it will kind of shift forward just a little bit. Okay, now if your relaxation factor equals to 1, relaxation factor equals to 1. If your relaxation factor equals to 1, then your change between the x old and the x new will be, well, is the same as when you have x new equals to x calc. It will be this full line over here. All right, this full line over here. Okay, this part I'm shading. Okay, so let's say if this, now let's say you have a situation where your iterations are traveling very slowly. The change over here is too small. Okay, too small. Now what you can do is you get your relaxation factor more than 1. Okay, you get omega. Okay, omega more than 1. So this is called over relaxation. So over relaxation, in this case, instead of slowing down the iteration, you speed it up. However, you do it, the trade-off is, of course, your equation, the rate at which, the equations themselves become more unstable. Now, where is this suitable? Okay, so let's say you have an equation like this. So 1 times 10 to the minus 5 z plus 1 times 10 to the minus 3 y plus 10. So let's say you have this kind of very, very stable equation. You see all these factors are so small. Then you can kind of afford to give these little coefficients a boost there. So you can say that omega here, let's say you want to multiply it by 500 times. Yeah. And it will still be okay because the coefficients here are still less than 1. Then you have your 1 minus omega x old. So this way your iterations speed forward very fast. Okay, so this is called over relaxation. So I mean, yeah, there's another way of viewing a relaxation factor, and here it is. Let's say this is your true value of x, and you are iterating, right? Now, remember every time we kind of guess forward, there's a certain length with which you can. There is a certain length with which the iteration moves forward. So this is maybe the nth guess. We talked about using maybe like the 11th guess, 12th guess, but I don't know how many guesses there are. So we have the nth guess over here. You want your iterations to eventually converge on the true value of x. So of course we will want to. Tendency is for x to move towards the true value of x. The iterations of x to move towards the true value of x. So let's say your nth plus 1th guess is here. N plus 1, right? Okay, so that's good. Usually the guess will kind of say, hey, I want to move somewhere here. But let's say again, because your system of equations was sort of bad, your distance to actually move forward is somewhere here. So yeah, you're moving in the right direction, but you're moving too much. So you have x n plus 2. And then this guy says, hey, I need to shift back to this direction. By how much? Maybe it will jump to here. So it's again moving in the right direction, but it's again jumping too much. So again, the distance in which the iteration kind of moves is too much. And then it kind of hovers around this point. And if the errors, like I was saying, grow in size, every time you iterate, it will get further and further away from this point. So your iterations will kind of oscillate. You'll go back and forth, you'll oscillate around the true value of x, but never actually get to the true value of x. In fact, sometimes it can blow up, as I'm talking about here, as in the errors get bigger and bigger. Errors being the deviation between your guess of x and the true value of x. So if the oscillations are growing, we call it a diverging solution. And a common terminology is for us to say that the solution blows up. Okay, blow up. All right, so the solution is blown up here. Okay, so again, the usefulness of relaxation factor is to say, hey, you're moving in the right direction, but let's slow down a bit. Let's under relaxation. So the n plus 1 guess under relaxation, maybe somewhere here, and n plus 2, the n plus 2 guess will be here, n plus 3 guess will be here, n plus 4 guess will be here, and then you will hover, you start hovering around the true value of x, right? But your residuals are so small that they pretty much fix on the true value of x if you set your relaxation factor right. So if you say you want to under relax, okay, let me under relax. You want to do an under relaxation, so the iterations kind of move forward slowly. They are less likely to miss this true value of x, and based on how the errors actually propagate, like I was talking in the last video, you can avoid this problem of having a diverging solution. Now, if you studied ordinary differential equations before, it is something known as a, if you have something like this, we will call it a stiff equation. So again, you can see this is a Wikipedia thing. So if we have this exact solution being this blue line here, and we have this we want to solve using Euler's method or what, and if your step size is too big, then you'll have this kind of diverging solution where you kind of have the thing oscillating around there. I will leave this link in the video so you can take a look at your own time. But that also shows, you know, what the importance of relaxation factor is, because you're saying we don't under relax, we want to we want to slow down your oscillations, or you want to slow down how fast the solution, the iteration of x is actually moving forward, so that you can get yourself closer to the true value. So a lot of numerical solvers, they have this problem of blowing up. So under relaxation is part of the solution, and definitely in OpenFOAM this is the case. So in case C1, you don't have this relaxation factor. So while we are cycling through the momentum equation more than one time every iteration, you may have this set of stiff equations. So the equations you're running through is correct. You want to run through the stiff equation, not the stiff equation. You want to run through the momentum equation more than once so that you can reiterate for a more stable solution. However, if you have this stiff problem where the system of equations is making you move the guess forward by so much that you actually miss the true value of x, then you're going to run into problems. So the way to do it is to set relaxation factors, as you can see here. So you can see for the field, for example, the pressure relaxation factor is 0.3. So every time, remember this, you have a pressure field and you have some system of pressures, you can have this omega, or the relaxation factor equals to less than 1. So this is, remember, under relaxation. So under relaxation makes the thing more stable, but a bit slower. But it's okay. It's okay to be slow as long as you get stable solution. Likewise, for the equations, you have the u, which is the velocity, k, k epsilon. This is a turbulence model. K is turbulent kinetic energy, and this is the turbulent, I can't remember, viscosity or something. I can't, eddy diffusivity, yes. So something along those lines, but you have relaxation factor of less than 1, which is 0.3 here. This will help to stabilize the calculation. As you can see, if we check KC2, we look at KC2 here according to this OpenFOAM guide, we see that the residuals are getting smaller and smaller. See, it's from 1 all the way down to 0.01 and then down to 1 times 10 to the power minus 5. So after 50 iterations, you see the first set of iterations, it kind of gets pretty small. So this is the right kind of relaxation factor to go for. And of course, if you can also have this option of setting your final relaxation factor to be, let's say this factor to be 1. And why would you want to do that? Well, if after 50 solutions, after 50 iterations, you kind of, hey, you guess like, hey, you more or less settle on a a solution already. If you want to reset this relaxation factor, or you want to say, hey, the errors are so small that even if you have a very bad system of equations, it doesn't really matter anyway. Yeah, so the bad system of equations doesn't matter. But, okay, I think I had a typo here. In front of xo, it should be 1 minus omega rather than omega. Right, here. Oops, sorry. So I have omega here, and I'll just repeat it for all of them. Oops. There you go. Last one. Okay, so that is that. And I'm doing only one set of iterations. So getting back to that, we're only doing one set of iterations so that the final for example, you have the final relaxation factor set as 1. So how does this work? If you have n outer correctors equals 50, meaning to say you iterate iterate this box 50 times. So at the 49th to the 50th iteration, instead of the relaxation factor being 0.3, it will be set at 1. So that's how it works. This is entirely optional, up to you. If you want to speed up your numerical scheme at the end, then yeah, be my guest. So in this paragraph, it says we introduce relaxation in a simple calculation between the time steps to obtain a smooth convergence rate. So yeah, of course, in OpenFOAM, there's you don't want to always go through the full 50 iterations. So there's a little bit of magic to that, to say that, hey, I don't want to move through the 50 iterations. So how can we get our exit this calculation before it reaches 50? So again, we have this thing called residual control. What it does here, it says that, hey, if your residuals, which I was talking about earlier, which is your residuals are the difference between the nth guess and the n plus 1th guess. So this is called the residual. The residuals it is not the difference between the nth guess and then the true value. This is actually called the error. Now, if this error blows up, then yeah, we talked about it before, it's a diverging case. So residual and error is different. So residual is the difference between the n and the n plus 1th guess. So if that becomes very, very small, below a certain tolerance, if it goes below a certain tolerance, and then you can say, okay, pretty much we have arrived at the answer. Okay, so if this is u, if the tolerance for u kind of gets below 1 times 10 to the power minus 5, or relative tolerance below 0, which it doesn't actually happen, or the pressure tolerance goes below 5 times 10 to the power minus 4, I mean the residuals, if the residuals of the pressure go below 5 times 10 to the power minus 4, and the residuals for u all go below 1 times 10 to the power minus 5, then okay, we stop the iterations. So for this case, we run a full 50 iterations according to these n outer correctors. You can see the iterations at the bottom here. This is the number 50. I'm clicking over here and just above this words table. There's 50, there's 100, 150 over here. So every time step there'll be 50 iterations. So yeah, it'll be 50 iterations, and then you'll go to the next time step or next time step, and then you'll go to 50 iterations. Next time step, run a full 50 iterations. Next time step, 50 iterations. So if you want to not have OpenFOAM do that, you can say, if it reaches this tolerance, if the residual reaches below these values, I want to move on to the next time step. You can absolutely do that. So the first time they move to there's almost a full 50 iterations being run. And then at the next time step, you don't have 50 iterations being run. You have like maybe 30 or 40 because the residuals here are being they reach a certain value, and then we exit the loop. Then we can go to the next time step. So again, not a full 50 iterations are being used, maybe less than 50. So see, Pimple, okay, for example, Pimple here converged in 28 iterations. So it's not a full 50 iterations. So it's controlled by this tolerance, right? This tolerance here is very important because, okay, it tells the OpenFOAM to move on to the next time step once your solution has more or less converged. So if you that means to say if you use this residual control to get to the next iteration, it means that at every time step your solution is more or less converged. So you don't want to, like, let's say you don't want to have a case where even after 50 iterations you don't converge your case, right? Let's say at 50 iterations your error is still pretty big and your residuals are still pretty big. You can kind of conclude that for that time step your OpenFOAM simulation has not converged. So if you want it to converge, you can set this and outer characters at a very high number, and this document recommends like 1000 or so, and your residual control says, okay, if you reach a tolerance of 1 times 10 to the power minus 5, if it reaches that value, then you can say, oh, stop, we can move to the next time step. So instead of being limited by these 50 iterations, and if you want it to be such that every time we move forward with the next iteration, we want the solution to be converged according to this tolerance you set. You want this to be the controlling factor in general, and if you want to do that, you set your tolerance here, but you set this number of outer characters to be very high, so that your iterations are controlled by this tolerance rather than these maximum iterations. If you do that, of course, it means that you can be sure that the velocity fields that you calculate are more or less the correct ones, so that you can be more confident of your calculations. So these are the basic things that we need to dabble with pimpleFoam. All right, these are the basic things we need to dabble with in pimpleFoam. So we can try setting up pimpleFoam in our GitHub case. All right, and again, this is what let me clear this up. I'm using my other computer, so we can go to the thin pipe flow snappy hex mesh, pimpleFoam snappy pipe, and go to my GitHub. Let me check. So we can go to my GitHub. It should be this thin pipe flow snappy hex mesh. So I'm going to start modifying the thin pipe flow snappy hex mesh on the next video onwards, just to see whether this pimpleFoam thing can actually work. Okay, so clear. So in the next video we can start looking at applying what we have learned, at least in theory. Okay, and you can apply what we learned in theory, and I highly recommend you get this mathematics, numerics, and OpenFOAM for more details, but we'll move on to more practical application in the next video. So credits to this guy who wrote the OpenFOAM guide, the Pimple algorithm, and of course he cited the mathematics, numerics, and derivation in the written by this guy. What is his name? This guy's name is Tobias Holzmann. So credits to them for going through the really in-depth stuff of OpenFOAM. I'm just here to try to put whatever they are saying in layman terms, so that it's a bit easier for us. So I post all this in the links about stiff equations, about mathematics derivation and OpenFOAM, the link, and you can download the 2.3 version for free. It's a free download. I highly recommend you go and get it as a reference for yourself. Okay, so yeah, in the next video we're gonna start looking at the pimpleFoam snappy pipe case. We can talk about it then. So it looks pretty exciting. We can start in the next video. Thanks for watching. I'll see you guys next time.